Hi, today we are going to see the topic moment of inertia of rigid bodies. Moment of inertia of rigid bodies. Before going into the rigid body calculation for moment of inertia, we should know something about kinetic energy of rotation. Basic kinetic energy formula you know, that is half mv square. In terms of rotational motion, what is the kinetic energy? That we have to calculate. So you consider a rigid body which is capable of rotating through an axis xo x dash. It is rotating like this. You have different particles having some mass. It is a rigid body. When you rotate the rigid body, the position of that particular particle will not be altered, fixed. So only it is called as a rigid body. Each particle has got a similar mass. Every particle here is at a distance of r1, r2, r3, etc. If we have n particles, means up to rn, mass of each particle is m. They are not identical, means we can take m1, m2, m3 up to mn. So, kinetic energy of rotation Er is equal to, basic formula for kinetic energy is half mv square. All the particles we are calculating. So sigma mr square, mv square. But v is equal to r omega. So I can write Er is equal to half m. Say for the first particle I am writing m1. V square means r1 square omega square. For the second particle, half m2 r2 square omega square, etc. Half mn rn square omega square. Okay. Why omega is constant, sir? When the rigid body is rotating, all the particles in the rigid body is rotating at a common speed, at common angular velocity. Omega is called angular velocity. So when the body is rotating about an axis, definitely the angular velocity of the system remains constant. So omega is constant here. So we can take out omega square by 2 as a common factor, m1 r1 square plus m2 r2 square, etc. mn rn square. So er is equal to omega square by 2. This is a summation series. On common term, summation series, where I ranges from 1 to n, mi ri square. R is the distance of the particular particle or a rigid body from the axis of rotation. This sigma I is equal to 1 to n mi ra square is called moment of inertia I. So half I omega square, where I is equal to sigma I is equal to 1 to n mi ra square is called moment of inertia of the rigid body. Unit, what is this? Mass. So it will be kilogram. Distance square, that is meter square. Kilogram meter square is a unit. Dimensional formula, mass capital M, R square, L square, ml square. Okay. So normal kinetic energy means half mv square. Rotational kinetic energy means half I omega square. So instead of m, it is replaced by I. Instead of v, it is replaced by omega. Whatever role mass plays in linear motion, moment of inertia plays in rotational motion. Same concept. Inertia, inability of a body to move by itself. Inability of a body to rotate by itself. Inertial body. Okay. Fine. Now we are going to talk about this R, that is R square value, that is known as radius of gyration. You can represent it by K. Ri square is equal to R1 square plus R2 square, etc., Rn square. Multiply and divide by n, where n is called the number of particles. Mk square. Nk square. Where k is called root of R1 square plus R2 square, etc., Rn square by n. Root means square distance of all the molecules, all the particles from the axis of rotation. Root means square distance of all the particles from the axis of rotation. That is called radius of gyration. It is nothing but a distance. Unit is meter, dimensional formula is L. As simple as that. Now we are going to calculate moment of inertia of different bodies. Moment of inertia of a uniform rod. Moment of inertia of a ring, uniform ring. Moment of inertia of a disc, circular disc. These three are the major. We will calculate the moment of inertia. Basic formula, moment of inertia is I is equal to sigma mr square. This is basic formula. Mass into distance square. Moment of inertia of a rod. Uniform rod. In the case of moment of inertia of a rod, you consider a rod of length L. We are going to calculate moment of inertia about an axis passing through its center and perpendicular to its length. So definitely this is L by 2, this is L by 2. You consider a small portion dx length which is at a distance of x from the center. The entire rod, you consider a small portion of the rod whose mass is dm. Calculate moment of inertia for this small mass. For the entire rod, then you integrate the equation. This is the basic concept. Consider a uniform rod of length L and mass capital M. Okay. Now we have to calculate the mass of this portion. Let dm be the small portion mass at a distance of x from the center. From the center, we are calculating that. Okay. Total mass is m. Total length is L. I want the mass for that small portion. Therefore, dm is equal to m by L into dx. Suppose the entire mass is 100 gram, total mass. Total length is 10 centimeter. I want mass for 2 centimeter. What is the formula? M by L into dx. Total mass is 100 grams. Total length is 10 centimeter. Calculate for 1 centimeter. 100 gram, 10 centimeter means 1 centimeter is 10 gram. So I can write dm is equal to 100 by 10 into for what length you want the mass. I need the mass for 2 centimeter multiplied by 2. That's what we have done here. So it will be 20 grams. 100 grams, 10 centimeter, 100 grams means 2 centimeter, 20 grams. Okay, fine. Therefore, moment of inertia di is equal to mass into distance square. Mass into distance square. What is the distance? Distance from the axis of rotation. That is x. So m by L into dx is the mass into x square is the distance square. Total moment of inertia. We have to integrate. Integral di is equal to integral m by L into x square dx. Integration means we should know the limit. This is the center. On the left, on the right of the center. So minus L by 2 to plus L by 2. Minus L by 2 to plus L by 2. Okay. Now, di is equal. Di integration is I. M by L is a constant. X square dx minus L by 2 to plus L by 2. X square dx. X square dx integration is x power n plus 1 by n plus 1. So I can write I is equal to m by L into x power 3 by 3 minus L by 2 to plus L by 2. Limit. So take this 3 outside, m by 3L. Instead of x, substitute upper limit, L by 2 the whole cube, minus instead of x, substitute the lower limit. Lower limit is minus L by 2. So minus of minus plus L by 2 the whole cube. L cube by 8 plus L cube by 8. 2L cube by 8. 2L cube by 8. That is 1 by 4. L cube by 4. ML cube by 4 into 3. 12L. So ML square by 12. 1L getting cancelled. The moment of inertia is m by 12 into L square or ml square by 12. Very important 5-mark question this is. Moment of inertia of a uniform rod. Okay. Next is moment of inertia of a uniform ring. Ring is different from disc. Ring is full hollow. This is uniform ring. Through the center, this is the axis of rotation. Say, for example, x, O, x dash as usual. The radius is r. We have to consider the small portion of the ring. Small portion of the disc we have calculated. Similarly, take small portion of the ring whose mass is dm, which is at a distance of r from the center, that is nothing but the radius. So let m be the mass of the ring. M be the mass of the ring. With radius r. Our aim is to calculate mass of this small portion. What is the basic calculation? Total mass by total length into length of that part. So what is that concept, sir? This is dx. There also we have taken dx. Here also that small portion length is dx. Let dm be the mass of the small portion. That is dm is equal to mass by length into the length what you want. Mass by length means it is circular ring. You imagine that you are opening here, so it will become a straight line. Close it means it becomes a circle. So 0 to the maximum is 2 pi r. So m by L, L here is 2 pi r. Into what length you want? We want the length of dx. Therefore, moment of inertia is di is equal to mass into distance square. What is mass? M by L, that is m by 2 pi r into dx into distance from the axis of rotation is r square. Total moment of inertia we have to integrate. Integral m by 2 pi r into r square into dx. Sir, here we have to put the limit. What limit we can use here? From this point to the entire circle. So 0 to 2 pi r is the limit. 0 to 2 pi r. So I is equal to 1 r get cancelled here. mr by 2 pi integral dx. Integral dx is x. limit 0 to 2 pi r. Correct? So, I is equal to mr by 2 pi upper limit minus lower limit. What is upper limit here? 2 pi r. Lower limit is 0. So 2 pi r minus 0. 2 pi cancels. You will get mr square. Moment of inertia of a uniform ring is I is equal to mr square. This is second. First we have seen about the uniform rod. Second thing, circular ring. Third one, uniform disc. Disc means it is a full solid. It is not hollow, it is a full solid. So here, XO X dash origin. Actually here, full disc you are considering. One circular ring, another circular ring, another circular ring. So many circular rings together only forms a disc. That means it is full solid. Ring means it is a part of a disc. So many rings put together fully, you call it as a circular disc. So, in the case of a disc, this portion is a ring, small portion, whose radius or distance is small r. Whereas, this distance is nothing but radius of the disc. This is the radius of the ring, what you are considering. You are considering only a small portion of the disc. That distance is nothing but the radius of the ring, small r. Radius of the disc is capital R. What is our primary aim? Calculate mass of the small portion. Then calculate the total mass into distance square. We call it as moment of inertia. Basic formula. So, let m be the mass of the disc. Of radius r. Let dm be the mass of small portion. That is, dm is equal to mass into mass by length. There we have calculated. In the case of a rod, in the case of a ring, we have put mass by length. It is not mass by length here. It is mass by area. Into that area, small portion area. Mass by area, total area is pi r square. Total area is pi r square. This portion distance is dr. This is from the center to this part distance is r. The thickness of that ring you call it as dr. So this is left hand side mass. Here what you have? Mass by area. So I have to multiply by area, then only I will get inequality. That is, inequality concept will arise otherwise. Left hand side mass means right hand side also should be having the unit of mass. What is the value? 2 pi r into dr. Area of that small portion. Moment of inertia of the small portion. What will you get? Di is equal to m by pi r square 2 pi r dr into square of the distance from the axis of rotation. Axis of rotation is x, o, x dash. From that, the square of the distance is r square. So I can write pi get cancelled 2m by r square into r cube dr. This is moment of inertia of the small portion. Total moment of inertia we have to calculate. Total moment of inertia. What is the formula? Integral di is equal to integral 2m by r square into r cube dr. Sir, previous cases for a rod, we have taken the limit as minus L by 2 to plus L by 2. In the case of a ring, we have taken 0 to 2 pi r. Here, from the center to the maximum, the distance is r. Simply 0 to r. Okay. So I is equal to 2m by r square. R cube dr. What is the value? R power 4 by 4. X power n plus 1 by n plus 1. Limit 0 to r. 4 and 2, 2 times m by 2r square. Upper limit r power 4 minus lower limit 0. R square r power 4 cancelled. You will get half mr square. So moment of inertia of a disk is mr square by 2. Moment of inertia of a ring is mr square. Half of that. Easily you can remember. We know the relation connecting kinetic energy and momentum. Kinetic energy is p square by 2m. P is called linear momentum. Like that, in rotational motion, what is the relation between kinetic energy and angular momentum L? That is linear momentum. This is angular momentum. Kinetic energy of rotation ER half I omega square. That's what we have derived. Multiply and divide by I. You are multiplying by I, you are dividing by I. We know angular momentum L is equal to I omega. Linear momentum is P is equal to mv. Angular momentum is L is equal to I omega. So I can write kinetic edge of rotation 1 by 2i I omega the whole square. So L square. L square by 2i. Linear motion kinetic energy is P square by 2m, where P is called mass into velocity. So instead of P square, here we have L square, 2m here 2i. So whatever role linear mass plays, same role rotational mass also, moment of inertia also plays. Okay. So these are the topics. today. Kinetic energy of rotation we have gone through. What is rotational kinetic energy we have proved? The value is half I omega square, where I is called the moment of inertia. Sigma I is equal to 1 to n mi Ri square. Then we have seen radius of gyration, that is root mean square distance, that is called k, radius of gyration, or also you can keep, no problem. Moment of inertia of a uniform rod, IR rod, what we have derived? ml square by 12, moment of inertia of a rod. For a ring, IR, this is for a rod, this is for a ring. mr square, and for the disk, moment of inertia of a disk, what we have? mr square by 2. Then we have seen the relation between kinetic energy and moment of inertia. ER is equal to L square by 2I. Correct? So these are the next topic in moment of inertia is theorems. Theorems in moment of inertia. Parallel axis theorem, perpendicular axis theorem. Two theorems we have. Parallel axis theorem. You consider an irregular shaped rigid body. This is the axis AB passing through the center of mass or center of gravity point, C. Consider one more axis, CD or DE. We have to calculate moment of inertia for this parallel axis by your parallel axis theorem. The distance between the two axes, you call it as D. Through the center of mass or center of gravity surrounding, there are so many particles at a different distance from the axis what you are considering. You consider one point here or one particle here, which is at a distance of x from the center of mass point. Let IC be the moment of inertia about an axis AB. About the center of mass, the moment of inertia is IC. Our aim is to calculate moment of inertia about the parallel axis. About the center of mass axis, we know already. About the parallel axis, we have to calculate. Okay. The distance between the two already we know. This is x and this distance is d. Moment of inertia about the parallel axis dE for the entire body I is equal to formula is mass into distance square for all the particles. So we have to write sigma. Mass of one particle is m. Distance from the axis of rotation. This is x, this is d. So I can write x plus d the whole square. So I is equal to sigma m x square plus d square plus 2xd. X square plus d square plus 2xd. So sigma m x square, sigma m d square plus sigma 2m xd. This term here is 0. Why it is 0? When you say AB is the axis passing through the center of mass point, here you are considering a particle only on the right hand side. By similarity, you have one more particle like this on the left hand side. So when you calculate this distance, it will become x minus d. The distance, the total distance is, this is d. So d minus x. Everywhere you will not get d plus x or x plus d. You may get somewhere d minus x also. In the case of d minus x equation, d minus x the whole square, d square plus x square minus 2xt term will come. So that minus 2xt and this plus 2xt will get cancelled. You have 500 particles having a mass m. Through the center of mass, when you take any axis, on the right you have 250, on the left you have 250. So these two get cancelled. So this term will become 0. Okay. So now, what is IC? Mass into distance square, capital M. Capital M is nothing but sigma M, mass of all the particles. So here I can write it as capital Mx square plus capital M d square. This is IC, this is md square. So the moment of inertia will be I is equal to IC plus md square. Sum of moment of inertia about the center of gravity or center of mass point and product of mass and square of the distance between the two axes. This is called parallel axis theorem of moment of inertia. Next, we are going to see perpendicular axis theorem. Here, we are going to consider a rectangular lamina having three different axes: X, Y, and Z. You are considering one particle here, which is at a distance of X from Y axis and Y from X axis. This is origin. Origin to this point, the distance, let us take it as R. Let m be the mass of the particle P which is at a distance of x from y-axis and y from x-axis. So moment of inertia about the third axis, about the z-axis perpendicular to the plane. This is horizontal xy, perpendicular plane. Z-axis we have to calculate. So for that, moment of inertia about z-axis is Iz is equal to sigma m r square. Here r square is equal to x square plus y square. So Iz is equal to sigma m x square plus y square. Sigma m x square plus sigma m y square. Sigma m is nothing but capital M x square, capital M y square. X is the distance from y-axis, mass into distance square. Y-axis, that is called the axis of rotation. So it will be Iy. You cannot write it as Ix because distance from which axis of rotation we have to calculate. Distance from y-axis. So Iy. Y is the distance from x-axis. So it will become Ix. So this is the moment of inertia of the rectangular lamina about three mutually perpendicular axes, x, y, and z. That is, Iz is equal to sum of the moment of inertia of the remaining two axes. That is Ix and Iy. Okay. So this is theorems of moment of inertia. We have relation of torque and moment of inertia. What is torque? Strictly speaking, torque is nothing but rotating force. Moment of a couple is nothing but a torque. So, torque tau actual formula is, it is a vector product of two vectors r and f. So, r cross f, rf sin theta. Maximum value means tau is equal to rf. Suppose you are calculating torque for the entire rigid body. For the entire rigid body, when you are considering, for a single particle means it is okay. For the entire rigid body, tau is equal to sigma r into f is equal to ma. But relation between linear acceleration and angular acceleration. Linear acceleration is a, angular acceleration is alpha. So we can write a is equal to r alpha. So I can write tau is equal to sigma m r. A is r alpha. So r square alpha. Already we have learned sigma mr square is equal to the moment of inertia. Mass into distance square is moment of inertia of that particular rigid body. So I can write tau is equal to I alpha, which is similar to now the equation F is equal to ma in normal linear motion. Rotational motion, torque. Linear motion, force. There, mass. Here, moment of inertia. Linear motion, acceleration. Angular motion, angular acceleration. Fine. Next. Tau is equal to I alpha. I want a relation connecting torque and angular momentum. Torque and moment of inertia with torque and angular acceleration you have written. We need the equation or we need the relation torque versus angular momentum. Why? In Newton's second law, what we have studied, rate of change of momentum, you call it as force. Like that, here we are going to prove rate of change of angular momentum is torque. Rate of change of momentum is called force. Here, rate of change of angular momentum, you call it as torque. So, what is alpha? Rate of change of angular velocity. Acceleration means rate of change of velocity. It is angular acceleration. So, rate of change of angular velocity. Therefore, tau is equal to I, alpha is d omega by dt. D by dt of, take I also inside, I omega. We know angular momentum is L. L is equal to I omega. So I can write tau is equal to dl by rate of change of angular momentum is equal to torque. Simple. Correct. Relation between torque and moment of inertia or torque and angular acceleration we have studied. Then torque with angular momentum also we have studied. Now we have to see conservation of angular momentum. In conservation of angular momentum, linear momentum conservation, what we have seen, in the absence of external force, the momentum, linear momentum of the system remains constant. Like that here, in the absence of external torque, the angular momentum of the system remains conserved, remains constant. What is the meaning? In the absence of external torque, that is tau is equal to dl by dt is equal to 0. Differentiation of a number, differentiation of something is equal to 0 means this something is called a constant. Here rate of change of angular momentum is 0, therefore L is a constant. That is L is equal to I omega is a constant. I proportional to 1 by omega. Moment of inertia and angular velocity both are inversely proportional. Greater the moment of inertia, lesser the angular velocity. Or lesser the moment of inertia, greater the angular velocity. I and omega are inversely proportional. Simple. What is moment of inertia? I is mr square. When r is greater, I is greater. So imagine a person holding a dumbbell in his hand. some weight. This is the axis of rotation. So he is extending in arms and rotating like this. When he is rotating by extending his arms, this is called axis of rotation. So from the axis of rotation till the end, this end, this is called the radius or the distance. Suppose when he is folding his arms and rotating, axis of rotation, this folding his arm, the distance is small. Distance is small means moment of inertia is small. Moment of inertia is small means what is the meaning? Angular velocity is more. So when the person is holding his hand, and then rotating means he can rotate faster because moment of inertia is lower. So angular velocity is more. But when he is extending his arms and rotating, what is happening here? Moment of inertia is more. So angular velocity is less. Okay. So this is the best example for conservation of angular momentum where we can prove I and omega are inversely proportional. Okay. Work done by the torque. Here you are applying a force, opposite side you are applying a force, the body will try to rotate. Equal and opposite forces, opening and closing of a pen cap, tap opening and closing, opening and closing of a lock. All these examples for moment of a force or moment of a couple. That is called torque. So when you apply a force simultaneously here and here, the body is about to rotate. For a small angle you consider, this is theta, this is also theta. Both are force. Here, after a time of t seconds, the body is moving or rotating through an angle theta. Force into perpendicular distance, you call it as torque. So torque is F into 2R. Force into perpendicular distance. F into 2R. What is actual concept of force? What is actual concept of work done? Work done is force into displacement. Here the displacement is this one. This is called the displacement. So F into this equation. This is radius R. F R theta. F into R theta. Similarly, this side, F into R theta. Generally, force into perpendicular distance means torque, but with rotating force, work done, we want to calculate. We don't want torque here. Work done by the torque, we have to calculate. Torque is F into 2R, but work done is F into R theta plus F into R theta. F into 2R into theta. F into 2R already we told it is torque into theta. So work done by the torque is W is equal to tau theta. In the case of linear motion, we know work done is nothing but force into displacement. Here, instead of force, tau, instead of theta, angular displacement. Instead of R, theta, angular displacement. Okay. So two different parts we have seen. First part, moment of inertia, kinetic energy of rotation, radius of gyration. Then three rigid bodies, moment of inertia we have seen. One, moment of inertia of a rod, moment of inertia of a ring, moment of inertia of a disk. This is part one. Same moment of inertia, second part, what we have seen is theorems of moment of inertia, parallel axis theorem and perpendicular axis theorem. Then what is called angular momentum and conservation of angular momentum. And finally, we have seen work done by the torque. Okay, so these are the topics of rotational motion. In that, we have studied about moment of inertia in detail. Thank you. We'll continue.